Hello, my dear students. So, once again, I welcome you all to another session of a very interesting chapter named as Solid State. So, in today's class, what are we going to do? We are going to talk about a very interesting thing that is nothing but packing efficiency in cubic unit cells. Yes, obviously, I'm going to be your host, I'm going to be your teacher for the lecture, and you need to understand we have already talked about what is packing. We've already talked about that during the packing, the particles are considered to be spherical particles for the ease of calculation. Getting the point? And now we need to understand that we have studied square closed packing, we have done hexagonal closed packing, we have done cubic closed packing. So out of these three packings, which unit cell or which packing has the best packing efficiency? But for that, we need to understand this term, what is packing efficiency? Correct? So let's go ahead and talk about what is packing efficiency. But before we jump into this topic, let's just give a very brief overview to the chapter, since it is almost the end of the chapter. So I thought let's just give you the flow of the chapter. The first thing we talked about was the characteristics of the solids, very important, wherein we talked about lots of characteristics, that the particles cannot move, they are rigid, solids are rigid, they are incompressible, lots of characteristics we already know since our earlier classes, and we have already done that in this chapter as well. Then we moved on to very important classification of the solids, wherein we talked about that there are two types of solids, that is crystalline solids and there are amorphous solids, and we talked about lots of difference points between these two solids. Correct? Then we told you that amorphous solids, most of the elements, they form crystalline solids. So amorphous solids are not of much use to us right now. So we went on to the crystalline solids and we talked about the four classification of crystalline solids. I'll just name them: metallic solids, ionic solids, covalent solids, and molecular solids. Right? So we talked about all these solids and we talked about their characteristics, we talked about their differences, forces acting between the particles, lots of things were talked about, right? So that is not what I'm going to teach over here. You can just go back, see that lecture and enjoy that lecture. Then we moved on to structure of solids, very important portion that was opened up from here, wherein we went deep inside at the molecular level of the structure and of the solid, and we talked about a very important thing, that was nothing but crystal and lattice. First thing we talked about this. From that lattice we brought about a very interesting term named as unit cell, the smallest repeating unit of the lattice. And from these unit cells we talked about very interestingly that there are fundamental unit cells, 7 types of fundamental unit cells, right? That table is going to be very important, with the relation between A, B and C and alpha, beta and gamma, because these are the 6 parameters on which the unit cells are classified. Perfect. Now this is very important to understand, bache. From this fundamental unit cells we talked about 14 Bravais lattices, right? We talked about 14 Bravais lattices. Very important, very important. Now this table, fundamental table, is going to be there 100%. There is going to be a question based on this. Yeah, Bravais lattices, I don't know if the question will be asked from this, but yes, you should have a knowledge of that from the 7 fundamental unit cells, which unit cells can be forming other types of unit cells as well. So this was the story of unit cells. Correct? Then we moved on to last lecture, where we moved on to packing in solids, where we talked about that the particles in the packing, they are considered to be spherical. Based on the packing, we talked about that there is one-dimensional packing, then we talked about there is two-dimensional packing, Two-dimensional packing was of two types: square closed packing and hexagonal closed packing. Please just close your eyes and start remembering the stuff that you've learned in the last lecture. From there we moved on to 3D packing, wherein square closed packing in 2D was converted to square closed packing in 3D. HCP packing, from there we saw that there were two types of packing: HCP packing in 3D and CCP packing in 3D, cubic closed packing, wherein I have also given you the difference between these two. Just a small, over here the unit cell that is formed is hexagonal, and over here it is FCC, face centered cubic unit cell. Perfect. Please, very important. Two voids. Voids is a very important term. Once again, there were two voids in 3D that we came along. That was tetrahedral void and octahedral void. See, I'm just giving you a brief of the chapter so that the things get recalled in your mind. We also told you a very important thumb rule. There was a very important thumb rule which I gave you, that if there are n atoms in the packing, there will be two n tetrahedral voids created and n octahedral voids created. So this is a tetrahedral void and this is octahedral voids created. Alright, so this was what we talked about till now, and today we are going to talk about packing efficiency. We are going to go continuation in this topic only, where we are going to basically talk about the packing efficiency. Packing efficiency, what is packing efficiency? In a minute you will come to know. After this, there are two theoretical topics left in the chapter, that is defects in the solids and some specific properties regarding solids, that is magnetic properties and electrical properties. Alright, so let's reveal for you what is packing efficiency. Now, before you understand this term, you need to understand a very important line, that in each type of packing you observed something. What was the observation? That all the space in the solid cannot be covered, right? Since the particles are spherical, there is going to be some empty spaces, some vacant spaces in the solid, correct? In between the constituent particles there is going to be some vacant spaces, and those vacant spaces are known as voids. Very important, voids, right? And these voids were classified into two: tetrahedral void and octahedral void. Tetrahedral void, if I talk about what is the coordination number of tetrahedral void, it is 4. It is surrounded by 4 constituent particles, 1, 2, 3 and 4, correct? Whereas if I talk about octahedral void, the coordination number is 6. See, 1, 2, 3, 4, 5 and 6, right? But since even though there are 6 constituent particles, it is known as octahedral. Why? You can just go back in the video and see that why it is known as octahedral. I have explained it, and you can comment down below in this video that why it is known as octahedral even if the coordination number is 6. I'll be looking forward to your comments in the video, but for now let's move ahead and let's talk about very interesting, what is packing efficiency. Then we have understood there are certain spaces, vacant spaces. Now those vacant spaces, they are not contributing in the packing, right? So what is packing efficiency? It is nothing but the percentage of total space filled by the particles. The percentage of total space filled by the particles in a particular type of packing or in a particular type of unit cell is known as packing efficiency. How can we calculate this? Very simple formula. Packing efficiency is nothing but total volume of atoms in a unit cell to ratio of the whole volume of the unit cell, correct? Cubic unit cell. We are going to talk about cubic unit cells only. So out of the whole volume, how much volume is being covered up by the particular atoms into 100, you get your packing efficiency. Is that clear? Perfect. Chal. Let's see one by one We are going to talk about very stringent to our syllabus. We are going to talk about cubic unit cells efficiency only. We are not going to talk about any another unit cells. Cubic unit cells के ऊपर ही पूरी कहानी चल रही है इस chapter में, and we are going to talk about that only. Correct? चल, let's quickly turn our page and give you the packing efficiency in cubic unit cells. Very simple, very easy. Understand? Let's first recall the simple cubic unit cell. You remember? Simple cubic unit cell looked something like this, wherein all the corners are occupied by the atoms. Corners of the unit cells are occupied by the atoms, and from those corners, only the 1/8 portion of the atom is inside the unit cell. So if I want to just take over here number of atoms in this type of unit cell, if I just talk, that is only 1, because there are 8 corner atoms and the sharing is with 8 unit cells, so the contribution of 8 corner atoms is only 1/8. So you get number of atoms in the unit cell as 1. So now how do we calculate packing efficiency? So सबसे पहले let's see volume of an atom. One atom is considered to be sphere, and sphere का volume क्या होता है? 4/3 pi r cube. Perfect है? Clear है ये चीज? For all the types of unit cells, volume of atom is going to remain constant. Of an atom, right? 4/3 pi r cube. Then we calculate the number of atoms in the unit cell. So you see, everything is going to get revised for you people. Yes, number of atoms in the unit cell is going to be 1 for our simple cubic unit cell. Yes? Okay, let's go ahead. Relation between edge length and radius of the atom, very simple. If this is your R, this is also your R, and this whole thing is your A. So you get the relation as A is equals to 2R. Correct? Simple? Alright. Then volume of the cubic unit cell. Now if the edge length over here is A, then the volume of the unit cell will be A cube. अच्छा, इस A cube, इस A की जगह पे हम यहाँ पर ये 2R रख दें, तो हमको यहाँ पर वॉल्यूम मिल जाएगा 8R cube. Why I am doing this? Because volume of the atom is in the terms of radius. So I have to take volume of the unit cell also in terms of radius. Perfect है? Clear है ये चीज? कोई दिक्कत इस चीज में? Good, बहुत बढ़िया. Let's go ahead and calculate the packing efficiency. Now, how many atoms are there in a simple cubic unit cell? 1. What is the volume of that one atom? That is 4/3 pi r cube. So what I do is 4/3 pi r cube divided by 8R cube into 100. Correct? R cube and R cube gets cancelled. 4 ones are 4 twos are. So you get the answer as pi/6 into 100. Yes, pi/6 into 100. और ये पाई कौन सा है भाई? ये पाई आपका मैथ्स वाला पाई ही है. तो इसको अगर आप डिवाइड बाय 6 करेंगे, दैट मीन्स इफ यू जस्ट take this 3.14 divided by 6 into 100, you get the packing efficiency as 52.4%. 52.4%. Alright, so I'll just write down over here packing efficiency. That means the total percentage filled by the atoms, the space filled by the atoms in a simple cubic unit cell is 52.4%. So if any packing is having a simple cubic unit cell, which was that? Square close packing, right? So in square close packing, the efficiency, the packing efficiency is 52.4. Correct? And very importantly, sometimes to confuse you, they might ask you how much empty space is left in simple square close packing. So वहाँ पर बच्चे 52.4 लिख के आ जाते हैं. गलत. This is the space which is filled, which is empty is 100 minus 52.4, and that is nothing but 47.6%. So you see almost 48% of the space in a simple cubic unit cell or in simple square closed packing, it is 48%, which is empty space, which is a lot of space, correct? And that's why simple square closed packing is, most of the elements, they do not want to go into square closed packing. Why? Because the efficiency is very low. Correct? Alright, let's clear the screen up and let's go to the next type of unit cell, that is nothing but face centered cubic unit cell. Very, very important. Once again, we'll go step by step only. Volume of the atom तो वही रहेगा, but इस बार number of the atoms will become 4. How? We know that there are 6 face centers shared by 2 unit cells, so half contribution, plus there are 8 corner atoms and 1/8 contribution. Calculate करेंगे, यहाँ पर 4 आएगा आपका. Relation between edge length and radius of the atom, आपको याद होगा, there is a face diagonal, right? So I particularly remember we have done this, wherein we took this triangle and we named it as, let's say, ABC. तो यहाँ से आपको मिल जाता था BC का स्क्वायर इज इक्वल्स टू AB का स्क्वायर प्लस AC का स्क्वायर, वेयर AB एंड AC आर A एंड A एज लेंथ. सो वहाँ से आपका रिलेशन निकला था. आई जस्ट राइट इट डाउन ओवर हियर, वेयरइन यू फाउंड आउट दैट this is nothing but R is equals to root 2 by 4A. This is what we found out, root 2 by 4A. And I particularly remember I had told you there also कि यहाँ पर इस 4 को, this is root 2 by 4A, R is equals to root 2 by 4A. This can also be written as, wherein we can just mention this 4 as root 2 into root 2 into root 2 into root 2. We can do that? Yes. And root 2 on the top, A. Root 2 cancel. Root 2 into root 2 is 2. So you get this as A by 2 root 2. You can get this also, right? So I can just say A is equals to 2 root 2 R. A is equals to 2 root 2 R. So I'll just rub this everything off over here, and we can simply write down this as A is equals to 2 root 2 R. सिंपल. देखो सब कुछ रिवाइज होता चला जाएगा. सो रिलेशन आ गया हमारे पास यहाँ पर बिटवीन द एज लेंथ एंड द रेडियस ऑफ द एटम. वॉल्यूम ऑफ द क्यूबिक यूनिट सेल तो ए क्यूब ही रहेगा, क्यूबिक यूनिट सेल है तो ए क्यूब ही रहेगा. बट इस ए की जगह पे अब मैं रखूंगा 2 रूट 2 का क्यूब एंड आर क्यूब. अच्छा, 2 का क्यूब 8, 2 का क्यूब इज 8 एंड रूट 2 का क्यूब इज 2 रूट 2, है ना. root 2 का cube is root 2 into root 2 into root 2 for our specially students who do not understand how to open up the powers. So this will be root 2 into root 2 2. So you get 16 root 2 as your answer, right? So 16 root 2 cube, 16 root 2 cube. I'll just write down this over here. This is 16 root 2 r cube. Is that okay? Now, putting this values in this formula over here, you get packing efficiency as very, very important. ध्यान से देखना ये चीज. You will get 4 into 4 by 3 pi r cube. Why 4 into 4 by 3? Because there are total 4 atoms divided by 16 root 2 r cube, where r cube and r cube get cancelled, and 4 ones are 4 fours are 4 and 4 gets cancelled. You get the answer as 3.14 divided by 3 root 2. And finally, when you solve this, you get the answer as approximately 74%. Yes, just see and try to solve this. Very, very important, very, very important. You get the answer as 74%. So this is the packing efficiency. This is the space which is filled by the atoms in a face centered or I would say in a cubic closed packing. Similarly, HCP packing also, when you will calculate, you will get 74%. So CCP and HCP, they both have same packing efficiency, and that's the highest packing efficiency in a given unit cell. That's the reason most of the elements you will observe, either they are hexagonally closed packed or they are cubic closed packed. Correct? So how much is empty space? 26%. How much is empty space? 26%. Clear है? Perfect है? Packing efficiency, very very important. Similarly, moving towards the last unit cell, that is body centered cubic unit cell. Once again, number of atoms 2. अब तो ड्रिल पता चल गया है. रेडियस और एज लेंथ के बीच में, अब याद करिएगा, यहाँ पर हमने एक यहाँ से डायगोनल लिया था और बॉडी डायगोनल इस तरीके से लिया था हमने, बॉडी डायगोनल, है ना. और जब हमने प्रूफ किया था तो हमको यहाँ पर मिला था r इज इक्वल्स टू √3/4a, ये मिला था. सो आई कैन जस्ट राइट डाउन दिस एज a इज इक्वल्स टू 4r/√3. करेक्ट है. वॉल्यूम ऑफ क्यूबिक यूनिट सेल तो a क्यूब ही रहेगा, बट a क्यूब की जगह पे मैं रख दूंगा 4/3 का क्यूब, सॉरी 4/√3 का क्यूब एंड r क्यूब. अच्छा, 4 का क्यूब निकालेंगे तो 64 आएगा, √3 का क्यूब निकालेंगे तो 3√3 आएगा, और r क्यूब तो है ही. तो यहाँ पर सिंपली मैं लिख देता हूँ 64/3√3 r क्यूब इज द वॉल्यूम ऑफ द क्यूबिक यूनिट सेल इन टर्म्स ऑफ r. करेक्ट है. चल, फिर हम यहाँ पर नीचे कैलकुलेट करेंगे पैकिंग एफिशिएंसी. तो चलो यहाँ पर पैकिंग एफिशिएंसी कैलकुलेट कर लेते हैं. we need to do 2 into 4/3 pi r cube divided by 64/3√3 r cube, है ना. चलो इसको सॉर्ट करते हैं. यहाँ आ जाएगा 2 into 4 into pi into r cube डिवाइडेड बाय, ये हो जाएगा 64 into 3. देखो ये 4/3 वाला 3 नीचे चला जाएगा और ये 3√3 वाला ऊपर चला जाएगा. सो ओवर हेयर 3√3 यू गेट ओवर हेयर एंड r क्यूब इज देयर. r क्यूब कैंसिल हो जाएगा, 3 और 3 कैंसिल हो जाएगा, 4 16s 2 8s. सो फाइनली you get the answer as √3/8 into 100. तो आप सिंपली जब √3/8 करेंगे तो आपको फाइनली आंसर क्या मिलेगा? बहुत सिंपली आंसर मिलेगा. जस्ट ऑब्जर्व दिस. हैव वी डन द कैलकुलेशंस परफेक्टली राइट? 2 into 4/3 pi r cube. Very nice. Okay, we have forgotten the pi over here. This is 3.14. So you multiply with 3.14, you get the answer as 67.9%. Approximately 68% is the packing efficiency in a body centered cubic unit cell. Perfect है. तो यहाँ पर हम एक काम करते हैं. सिंपल क्यूबिक यूनिट सेल के अंदर आपका आया था 52.4%. बॉडी सेंटर्ड क्यूबिक यूनिट सेल के अंदर आया 68%. एंड फेस सेंटर्ड क्यूबिक यूनिट सेल और आई वुड से हेक्सागोनल क्लोज्ड पैकिंग के अंदर या हेक्सागोनल यूनिट सेल के अंदर आपका आंसर आएगा 74%. सो बेस्ट पैकिंग एफिशिएंसी यू गेट इनटू एफसीसी यूनिट सेल. और इसी के बेसिस पे एमसीक्यू क्वेश्चंस आता है कई बार. अरेंज simple cubic BCC and FCC in increasing order of their packing efficiency or decreasing order of their packing efficiency. So the values are important. Nobody is going to tell you to derive this. Ye derivation is not going to be a part of your question asking. But yes, these numbers, they are going to perfectly trouble you and they are going to make you understand, make you answer such MCQ questions. Correct? So with this, the packing of solids is over, and over here one more portion of solid state chapter is complete. So we are left with only two portions, that is defects in solids and certain specific properties related to solid, that is magnetic properties and the electrical properties of the solid. Alright, so let's meet up in the next class, next lecture. with more energy, more smile. Till then, please be positive, take care of yourself, and bye bye.